Suppose we flip a fair coin n times and we let x be the total number of heads. We already have an intuitive answer for the expected value, right? So since the coin is fair, we expect about half the tosses to be around n over 2, right? But now we want to ask a more refined question. How far from this expected value should we expect the number of heads to be? So for example, if we toss a coin 100 times, we expect around 50 heads, but getting exactly 50 is not guaranteed, right? We might get 47, 54, 61, right? So we want to understand the typical amount of variation around the expected value. And so to do that, we first need to describe the random variable x a little bit more systematically. And so that's going to lead us to something called Bernoulli trials and binomial random variables. So a Bernoulli trial is a random experiment with only two possible outcomes. So we usually call the outcomes success and failure. And so a Bernoulli random variable with parameter p, and which we denote in this way. So we'll say that it's a random variable that has this parameter, Bernoulli parameter p, if you get a success, which we can denote by 1, a success with probability p, and the failure with probability 1 minus p. And so in this notation, when a fair coin toss is just a Bernoulli trial with parameter p equal to half, right? Okay, so now let's compute expectation and variance of our Bernoulli. So once again, a Bernoulli variable, so x is Bernoulli with parameter p if it's 1 with probability p, 0 with probability 1 minus p. And so what is the expected value of this? So the expected value of x then is going to be 1 with probability p plus 0 with probability 1 minus p, and this gives you just equal to p, right? What is the variance of, so what is going to be the variance of x? So remember that the variance, you can write it as the expectation of x squared minus the expectation of x this squared, right? So we need to compute the expectation of x squared. So the expectation of x squared will be 1 squared times p plus 0 squared times 1 minus p. And so this will be equal to p. And so that means that the variance of x will be equal to p minus p squared. And so this will be equal to, you can also write it as p 1 minus p. And so this gives us our variance. So as an example for our fair coin, so for fair coin, p is equal to half, and then the expected value is equal to half, and the variance of x is equal to half minus half squared, which is 1/4 here. So wait a second. Oh, sorry. Half minus 1/4. Sorry, I was looking at the other formula. So it's half minus 1/4, which is equal to just 1/4. I was looking at the other. You can also write it as half times 1 minus half. And so this will just be half times half, which will be 1/4. So the same thing. Okay, so this is what a Bernoulli P is. But many times what you're interested in when you talk about like tossing many coins, and that's called a Bernoulli trial. So what we want to do is we want to count the number of successes in many independent trials, right? So for example, if we flip a coin n times, we want to count how many heads occur. And so if you have x1, x2, xn, all of them independent Bernoullis with success probability p, then the random variable x here, which is the sum of them, is called a binomial random variable. And so we say that x is binomial and it has two parameters, n and p. So x is binomial n and p if x is a sum of n Bernoullis, each of the Bernoullis with success probability p. And so if p is equal to half, then this is just tossing n coins with probability half of heads. If p is equal to a quarter, then it's tossing n coins with probability 1/4 of heads, right? And so let's look at the binomial distribution and compute things exactly. So if x is binomial np, and this counts the successes, so we have n independent Bernoulli trials, what is the probability of exactly having k successes, right? So how can you have exactly k successes? So to have exactly k successes, of course, you have to have n minus k failures. And since each success occurs with probability p, we know that each failure occurs with probability 1 minus p. And so the probability of one particular arrangement of k successes and n minus k failures, it has probability p to the power of k, 1 minus p to the n minus k. So this is having k successes and having 1 minus p n minus k failures. And since there are exactly n choose k ways to select which one of the k's were successful, then the probability in general is going to be the probability that you have exactly k successes in a binomial will be n choose k, p to the k, 1 minus p to the n minus k. And the reason this is called a binomial distribution is because you have this binomial here, right? Okay. So with that, let's compute the expectation and variance of the binomial. So let x be binomial with parameters n and p. So what does that mean? That means that x is going to be the sum of n independent Bernoulli trials, and each of these is going to be Bernoulli with probability of success p. So let's compute this. So what is the expectation of x? Well, we already saw that the expectation of a sum is the sum of the expectation. So this will just be the sum of the expectations of each one of these, I equal to 1 to n. But we saw before that the expectation of a Bernoulli with parameter p is just p. So this is just the summation of p, and summing p n times is just n times p. So the expected value of the binomial is going to be n times p. And so now, what is the variance? So the variance of x, so we saw that when the sum is of independent, so we saw that the sum of independence, then the variance of the sum is the sum of the variances. So this means that this is going to be also the summation of the variances of each xi, I equal to 1 to n. And we saw that the variance of a Bernoulli, so the variance of the Bernoulli was this p 1 minus p, and so it's going to be n times that. So it's going to be n times p 1 minus p.